Morning. I'd like to start with a little debrief about your homework assignment. I think there's a lot of stress coming through the internet over the weekend, and I thought maybe the best thing to do would be to first, before we get started on the material today, just to briefly go over the requirements in terms of work for the course, which some of you have been emailing me about, and so I thought it might be best to address everyone in the class all together. So I want to remind you that there are 8 homework assignments and that your 2 lowest scores will be dropped. So if you really feel like you had a very tough time on your first assignment, don't worry too much. The other thing is I want to say about the first assignment was there are 2 things going on in your first assignment. One was to get started with using visualization for understanding distributions. And so this notion of statistical reasoning and statistical thinking was a big part of the assignment. An equally big part was to get up to speed in using R. And if that should sort of start tapering off as you get more practice using R. So some of what you were feeling in your first, or experiencing in your first assignment was the, getting started and how to think about using R to analyze data. One student sent me 2 emails over the weekend, and I won't, this person will remain anonymous, but I think it's a very good example of what process maybe all of you are going to go through in terms of learning R. So at one point, this person sent me an email saying, I'm really doubting whether I can proceed in this class. I have spent 6 hours on the homework, and I only have partial answers to the first 2 questions. I'm struggling a lot, and please give me some advice on what to do. And then 3 hours later, they sent me another email saying, ignore that first email. It clicked. I really get it. I understand what to do. I'm off to a good start. And so maybe it hasn't clicked for all of you yet, but I am expecting that it will click for you very soon in terms of how to use R to express your statistical ideas. So there are also, I've heard through the GSIs, there's some questions about the quizzes and what is a quiz going to be like, and there's real concern that you'll be writing code in the quizzes. And the quizzes will happen in section, but I think that it's never a good idea, even in, let's say, a programming class, to have people write code on paper that should be syntactically correct. And so the quizzes will not be expecting you to write code that we could then type into R and have it run and be syntax free. They'll focus much more on the kinds of issues that you're facing with, for example, the first homework assignment. Just as an example, it doesn't mean this will be on the quiz or on a quiz, but the kind of statistical reasoning that you needed to do in order to analyze the distribution of birth weights or compare the distribution of birth weights between smokers and non-smokers. So I think it would be good to open the floor up to questions about the work, if you have any. Yes, in the back? When will the quizzes be? Not yet determined. My guess is that the first one will probably be in about 4 weeks, maybe 5 weeks. Right. Any other questions? I'm going to introduce your second homework assignment. It's already been posted. I'll introduce your second homework assignment in class as well as in section. You've maybe already heard about it in section yesterday, and you'll be starting it in section tomorrow. And on Friday, I'm going to also cover it as well. And I'm hoping you're going to have a lot of fun with this. It's one plot that you're producing, just one plot. And it's going to be a beautiful plot. And you're going to be working with a partner to produce this plot. and your plot's going to tell a story. And I'll give you a demo of how I would do that on Friday. If there aren't any other questions, I thought I'd get started. So I'm posting the reading assignments under the syllabus button on BSpace. And so the reading assignment for this week was posted on the weekend, and it's to read the first 35 or 40 pages in the reader. And let me say, it's a very easy read in the sense that about half of those 40 pages are pictures to look at. What we're going to focus on now for the next 2 weeks is how to make really much more informative, clear, beautiful plots that uncover the structure and a story in the data. So I'm going to start with that today. And I'm going to start by revisiting the homework assignment that you had that was due yesterday, and I'm going to change the questions, but hopefully you'll recognize that the structure of the assignment the structure of what we're about to do is very similar to what you've already been working with for the birth weights. But instead we're going to look at body mass index for the mothers of the babies. So we want to sort of uncover the distribution of body mass index for women in the 1960s who had a baby at the Kaiser Hospital. So many of you will maybe have experimented already with the variable called WT, which stands for the mother's weight at the time she got pregnant. And HT, which is the mother's height. Body mass index is a way to combine height and weight to come up with a single number, which has been used as an indicator for whether you're underweight, average weight, overweight, or obese. And the formula, if we are working, I don't know, can you see that? The formula, if we're working in the units of pounds and inches, is your weight in pounds times 703 divided by your height in inches squared. And then there are cutoffs for this, and if you're 30 or above, you're considered obese. If you're 18 and a half or below, you're considered underweight. And I believe 25 is the cutoff for 18 and a half to 25 is for normal or average weight, and 25 to 30 is overweight. So we're going to ask the question, let's explore the distribution of BMI for these women. Let's start by asking the questions, what kind of variable is BMI? Is it nominal, ordinal, interval, or ratio? What do you think? Yes? Ratio, why? Because actually you can almost see a ratio in there, is what you're thinking. That's a good point. And if you also think about height and weight, are they ratio or interval data? Yes?
Maybe because things like double the weight, things like that make sense.
So, right, as well, if we think about it in terms of to go from 20 to 25 is a 25% increase, so it makes sense to think about this as ratio. What were you going to say?
I was just going to say, I was thinking that it might be interval, because you're not really going to tell somebody, the ratio is like something like twice as large as something else, or 3 times as large as something else.
That's a very good point. Most of the time that we are going to use BMI, we're going to look at differences. We want to know how far away are we from one of those boundary points. Am I overweight or not? And that's going to be looking at a difference, which suggests an interval. But remember, ratio includes interval.
Okay.
And so, yes, intervals are really important in BMI, but it also can make sense to look at a fraction of a increase or decrease as well. Okay, so let's make a density plot. So what I've done is I've already posted on BSpace all of the code that I'm using today, and I'm going to run through this transcript, and part of what I'm going to do, I'm going to try and address two things at once. One is sort of how do we go about answering these questions using R to make these plots, and how do we think about these distributions? So it's sort of along the same lines of what we've been talking about already. And the other is a focus on how do we sort of fix up our plots to make them look better and contain more information. And to get started with that, I want to take a look at this one plot for BMI that I've already made and introduce some terminology. So there are terms that we use when we're speaking about the pieces or elements in a plot that it would be good if we all had those common words. So in particular, this whole white screen is the canvas. So oftentimes we think about these things from using painter's terms. So this is called a canvas. Then the rectangular area here is called the scale region or the plotting region. Notice that the density plots that I have there's this little gap between the lowest point and the scale itself. And the same along the vertical direction. This is so that the data region is within the scale or plotting region. And the reason why we do that is so that if we're plotting points or have some particular feature in our data, we don't want it to be obscured by the scale or the axes. And so typically we have our scale, which is this box, and then within that plotting region, we have the actual data region. Okay, these guys here, these little lines, are tick marks. And the 15, 20, 25, 30, 35, 40 are tick mark labels. There are 6 of them here, and there's no exact number that makes the perfect plot, but roughly between 3 and 10 is a good number of tick marks to have on your plot. Likewise, for the vertical direction, we have tick marks and tick mark labels. The line here is called either the scale, the horizontal scale, or we often call it the x-axis. And the vertical line is called the vertical scale, or sometimes the y-axis. We have to be careful when we use x and y, because those are not necessarily the names of the variables that we're using to plot. So in this particular case, the x-axis is the BMI axis, and the y-axis is the density axis. The reason why the word scale is used is to let you know that you're trying to figure out what scale is being used to plot the data. The plotting symbols in this case are these curves. Sometimes a plotting symbol could be points or circles or stars. In this case, the plotting symbol are curves. We see that there are 2 colors here, blue and green. The legend in the upper right corner tells us that blue stands for smokers and green stands for non-smokers. So legend and key are used pretty much interchangeably. And here we have a legend for color. This gray line, vertical line, is called a reference line. We can have horizontal or vertical reference lines, and we can also have reference points. This one in particular goes down to 30 BMI, and so it's a reference for you to see roughly what proportion of these women or mothers are considered obese. And this text here, obese, is literally that. It's text that we have in the data region. Up top, BMI for mothers of Kaiser babies is the title for our plot. And down here on the x-axis, BMI is our label for the horizontal scale, and density is our label for the vertical scale. So let me stop there and ask if you have any questions. No? Yes? Good question. How can I put those two densities in the same scale region? We're going to get to that. So in a way, I'm showing you my end product, and now we're going to go into R and show you how I did it. And how I made all of these plots, or excuse me, all of these pieces to the plots, the titles, the axis labels, the legends, the colors, all of that is going to be the subject of today's lecture. Yes?
How can you determine whether or not you put a scale or tick marks on the, adding the scale on the right-hand side?
So your question was, can you control it? Is that what you're saying?
No, just when should or shouldn't you?
It's always good to have scales in general.
On the,
Oh, I'm sorry, on the right-hand side. Thank you. So very good point. I haven't even shown this, but you can put scales along, tick marks along the top line and tick marks along the right-hand line. You don't have to be restricted to only have tick marks and tick mark labels in the conventional bottom and left-hand side. And in particular, you want to do that, especially on the right-hand side, if there's data on the right-hand side that you want to call attention to and make sure people can easily tell what those values are. And R can do that for you automatically. So those are some of the commands. We're not going to get to all of them today, but those are some of the commands you're going to learn to use in the next couple weeks. Yes?
How do you call reference line R?
I'm going to show you that. So today, although I will say the reference line is a terminology that we're using, and you can put any kind of line on a plot with a call to a function called AB line, and you'll see that in a few seconds. Anything else? So those are the terms. And what we're going to be focusing on are sort of two basic principles. One's called clear vision, and the other's called clear understanding. And that's what the subject of the reading's about, is how do you make sure that you can really, the point of clear vision is for you to see the data, not get hung up in lots of extra stuff. For example, we could have put a little JPEG image of an obese woman on one side and a skinny woman on the other, and that doesn't really add any extra context to this particular plot. We could have had roughly 30 tick marks on the horizontal axis for every single unit of BMI, and that doesn't necessarily help you sort of see the underlying distribution of BMI. So there are lots of ways to put extra information on a plot, and the idea is to focus on the data and make the plot very data rich, meaning lots of information, but to not obscure the vision with sort of unnecessary, superfluous information, tick marks, labels, text, etc. Okay, so let's get started. Here's my R session. Let me see if I can make the I'm trying to make the typeset bigger. And I'm going to make my console really tiny so that, one, you can see plots appear, and two, so you can see what I'm typing more easily. All right, so the first thing we have to do is load the data, and I've already done that, and I must admit I don't believe I'm on the web right now, so I'm going to assume that I have loaded the data already, and I can check to see if that's the case by looking at the head of the data frame called infants and see that, yes, indeed, I have it there. And now I need to compute BMI. BMI is not part of the data frame. It's a new vector that I want to create, and I'm going to call it BMI. And remember, its definition was that it should be the weight, so infants dollar weight times 703. Is there a problem? Thank you. I like that. It call out my mistakes right away, because that way it'll avoid having to wait until I get the return from R to say, I've never heard of anything called infants with 2 Fs, divided by height squared. And so I now have BMI if I want to check to see what it looks like. I can look at the first 6 observations. If I want to see more information than that, I could do a simple summary of it and see, let me ask you, what do you see here? Name a few things that you automatically think might be something of interest. There are 39 NAs, so you guys have all been stung by that. You know that you're going to have to do something special for the NAs. That's right. What else? Yes?
The 15.66 minimum?
Yes, 15 is the minimum.
High for a minimum, honestly. Because I don't
Well,
think-
remember, 18.5 and lower is underweight.
What now?
18 and a half and lower is underweight. So that person's underweight. Also, remember, what's our population here? Women who, yes, although their weight, there is the weight that they reported at the time they went to Kaiser for their first checkup. So you're unlikely to have a really, really underweight woman who's pregnant. So yes? The max seems pretty big. 40? Why do you think that seems big? Right. So you're thinking that it's big because if I'm looking at where the third quartile is, it's like almost as far again to get to the max. And that should immediately tell you that either there are a few outliers or there's a really long right tail. This got me thinking about what's the BMI distribution like for people today? And this is similar to what I'm going to ask you to do, is to bring in extra information that will help you interpret what's going on with these data better. And so I went to the web, and I did a search on BMI obese women, and came to the CDC website. So another point is to be careful where you get your data from. The CDC is the Centers for Disease Control. So it's a U.S. Government organization, and chances are you can trust the data that you see on the CDC. So this is quite interesting. They actually have this little plot of the United States, a little map, and they've got the range for BMI, or for the percent that are obese. So the percent of the adult population, if you can read that, it's cut off a little bit. The percent of the adult population which have a BMI 30 or higher. And there's a lot of missing data. Those are the white states. California is not missing. And we see that California had fewer than 10% of the adults falling into the obese category. And you can page through this. You can say next, and you see 1986. And so I'm going to click this button a few times, 87, 88, 90, 91. So notice we're now in the 10 to 14%. Look at what's happening to the United States, 98, 99, 2000. California just hit 20 to 24%. 2004, and there we are. We're up to 2004, and we're in the 20 to 24%. And that's over 20 years. Isn't that amazing? So our data are from the 60s. Okay? So if we scroll down here, it's got every state and the obesity rates in 2009. California is right here at 24.8. So nearly a quarter of Californians are in the obese category. Compared to some states, though, we're doing pretty well. Look at Mississippi at 34%. The state with the least, I don't know, can you find it? Alaska's looking pretty good. Hawaii, Colorado, you know, have you ever been to Colorado? there are a lot of people that really care about exercise, and maybe that's why. Yeah. Anyway, so there's some context that you could then you can then bring to your interpretation of these data, and you could even possibly add this to a plot that you're making. So I thought that was kind of interesting. All right, so let's go back to our problem, is to look at the distribution of BMI. So we can immediately say plot of density of BMI and hit return, and we get an error that you should all be familiar with. Error in density.default BMI, X contains missing values. And we say, okay, we can look in the help for density. So notice it's telling us that the error is not in the plot function, the error is in the density function. We could do help on density to figure out what's going on, but you guys all know that what I really have to say is get rid of those missing values. And then I've got a plot of the density. So this doesn't look like the plot that I started out with. This is the default plot that R gives you. And we see that it tells us we've got about 1,200 women, and the bandwidth that's being used to smooth this is about 0.56. The title is actually kind of the density call, or the call to the density plot. Okay, so how do I go about figuring out how many women are, so briefly, we've already discussed this, is that it looks like we have what? I want to hear you tell me. There are certain things to look at. There's modes. We have a what distribution? Unimodal, bimodal, unimodal distribution with a main mode around. Good. 20, 21. And it is symmetric or skewed. It is skewed. And it has a short or long tails. It has a long right tail and a short left tail. Okay. And a very long tail where we would say there are a lot of women above 25 in term, well, the long tail is saying we've got a lot of women above 25 in terms of BMI. But what about the proportion above 30? So really quickly, how do we figure out what proportion is above 30? We know that with a density plot, that should be the area under the curve above 30. How do we figure out what that is? How do we figure out what proportion are above 30? I don't think we've talked about this really up until this point. So we need to know something about what are called quantiles. Quantiles are, does anybody know what a quantile is? No? Yes? The median is a quantile, that's right. It's the 0.5 quantile. It's the point at which half the data are below and half the data are above. Okay? What's another one? The 25th and the 75th quartile. That's the points at which 25% of the data are below and or 75% of the data are below. You can define a quartile for all sorts of different values. I have a little story here that we'll go through really quickly about quartiles and quantiles, and then we'll get back to our main show. So numeric summaries of quantitative data. Here are some examples of quantiles for birth weight. So now we're switching gears a little bit to look at birth weight. 105 ounces is such that if we look at the area below the density plot to the left of 105, we get 20%. So it's a point, it's 0.2 or 20% of the data are below 105. The median, as someone pointed out already, is the 50%, where half the population is below this point and half is above. That's 120 ounces. The 90th, 142 is the 90th percentile, and 163 is at 99. So there's A little bit of language here in terms of percentile versus quantile. If we have the actual unit of measurement, such as 142 ounces, we ask what percentile is that, and that tells us that 90 percentile says that the measurement 142 is at the 90th percentile. We can then flip it around and say, I want to know what the 90th or the 0.9 quantile is. So I'm fixed on the number 0.9. Now tell me what measurement in ounces that corresponds to. So that's the sort of interchangeability between percentile and quantile. It sort of depends on which is your starting point. So if you're starting with 0.9, that's the quantile, and then that you're after, and then you get the value 142. If you're starting with 142, then you say, oh, that's the 90th percentile. So briefly, we can have any kind of quantile we can ask for between 0 and 1. In particular, we might want to look at, for example, the 0.01 quantile of birth weight is 71 ounces. And there are 13 babies with a birth weight under 71. If we look at 13 divided by the total number of babies we have, 1236, we get roughly 1%. The box plot is a way to summarize these, some of the quantiles that we see a lot, and those are the lower quartile, that's with an R, not an N, the median, and the upper quartile. So the box plot is a visual way of giving you a summary of a distribution. It's not the same as a density plot, and we're going to talk in a minute about how it's different. But for our birth weight data, the minimum is 55 ounces. The lower quartile, which is the 0.25 quartile, is 109. The median's 120. The upper quartile, the 0.75 quantile, is 131. And the max is 176. So what's a box plot do? It makes a box, can go either vertical or horizontal, where in our case it's vertical. The lower edge of the box is located at the lower quartile. The upper edge of the box is located at the upper quartile. And the median is a line that goes through the box. Then we draw what are called whiskers. Oftentimes these are called box and whisker plots. We draw whiskers out of each side of the box. And they go all the way out to about, in each direction, about 1.5 times the interquartile distance, or the interquartile range. That's, in our case, the interquartile is from 109 to 131, which is 22. So it goes out 1.5 times that, which would be 33. So it goes out 33 above the upper quartile and looks back to find the first data point, and that's where it draws the whisker. Down below, it goes down 33 until it finds, and then looks back up until it finds the first observation, and that's the bottom whisker. Then there's still points that could be outside that range, and those are marked with circles or stars or something like that, to let you know that those might be unusually large or unusually small. So I have a couple questions for you. How do you think you can tell symmetry or skewness from looking at a box and whisker plot? Yeah?
Would it be the length of the whisker and then how centered the little line is in the box?
It would be both of those things. He said it would be the length of the whiskers. So if one whisker is really long in comparison to the other, that's kind of indicating to you that there might be a long tail and a short tail. And where is that line for the median in the box? Is it smack in the middle, or is it really close to the lower quartile or the upper quartile? If it's smack in the middle, that's kind of indicating symmetry. Was someone else going to say something? And what do you and then those circles would be potential outliers. So there we go. That we just talked about this, the lower quartile, upper quartile, median, and the whiskers. Questions for you. What can you not see in a box and whisker plot that you can see in a density plot? So this is sort of a cartoon of a in a way, a box plot is sort of a cartoon of a density plot. Cartoon meaning it doesn't show you all the features. It just kind of summarizes a few of them, and you could miss some really important features. Let's see if someone else has yes? You can't see the mode. In fact, you can't see the modes. So it could be bimodal and you wouldn't know it. And just because it's symmetric, meaning the medians between the upper and lower quartile, doesn't mean that's where the mode is. You could have something that's bimodal and perfectly symmetric, and the median would be right in the middle where there's no mode at all. Okay, what were you going to say? Yeah. Modes, same thing. Gaps. Can you see gaps in the data? No. So there are a lot of things you can't see in a box plot. Modes you cannot see, gaps you cannot see. Outliers you do get a sense of whether or not they're outliers. Symmetry you do get a hint of symmetry. You could work really hard to come up with an example that wasn't symmetric but looked symmetric in a box plot. You can imagine doing that, right? Where you can sort of fiddle to make sure that where the lower quartile and upper quartile are and the tails, etc. And tails, you get a pretty good idea as to the size of the tails. All right, so that's a really quick introduction to quantiles and box plots. And now we're going to go back to our problem at hand. All right, so we can, in fact, I can make up, let's say I want to figure out what all the quantiles are. There's a function in R called SEQ for sequence. I can go 0.01, that's my starting point, 0.99, my ending point, and by 0.01. So I've now created a vector, we can look at it, of 0.01, 0.02, 0.03, etc. And I can pass that to the quantile function, so along with my BMI. So I will say, here's the data, BMI, that I want you to use to find my quantiles. And here are the quantiles that I'm looking for. And it tells me, you've got NAs. I'm not going to give you any unless you tell me what you want to do with it. So I say NA.RM equals true. And there they go. So here they all are. So at 17, BMI of 17 is at 1%, meaning 1% of our data are 17 or lower. 17.38 is 2%, etc. Tell me where the obese line is. What percentage of women are obese? 3%, because you see that 29.9978 is right at the 97%. So you'll have 3% above, 97% below, and we only have 3% of the women as reporting a BMI on the obese side. That's so different than today in California, there being roughly 24% of the population obese. All right, so let's now move on to our next question, which asks us to, I can bring it up. We've done what's the difference in BMI for the women who smoke and those who do not smoke? Question in the back. Uh-huh. You can put any numbers you want in there between, your beginning point has to be 0 or above, and your end point, I'm sorry. Excuse me, I was answering for the quantile question. The SEQ function is really handy in R. It can create any kind of sequence of numbers. You give it a starting point, an ending point, and how big you want the increments to be. I determined that I wanted to start at 0.01 because I thought, let me just figure out what all the quantiles are from 0.01 to 0.99, and then I'm going to look for 30. So I just wanted to sort of cut it up into equally spaced intervals from 0 to 1. If you're looking for quantiles, yes, that's right. And there was one more question. Yes?
So when QS was basically like
Thank you. That's right. QS is a vector that I've made. Exactly. And BMI is another vector I made. So now we're going to get to making the actual plot that we started off with. And let me ask you, how should I go about doing that, comparing the BMI for the smokers and the BMI for the non-smokers? What have you done to do that? What would you do? Yes?
Create two new variables and subset the smoking to now the estimation.
So create two new variables. One will have what in it? A subset of? Those are the, okay, we want to look at the non-smokers. And what is it? What's the information we want to keep? Their BMI. That's right. So what I'm doing is I'm subsetting BMI. Right? I'm taking a subset of BMI, and I'm doing the subset according to whether they smoke or not. So I'm going to do the smokers first. So I would say BMI smoke. So notice my naming convention. I'm letting me know, so I don't get confused in the future, that this is still BMI, and it's a subset. It's the subset of smokers. So BMI smoke equals subset BMI, and you're telling me I could use the smoke category, categorical variable, infant smoke, and equal now. And I'm going to say, what else could I include in my subset? How about until pregnant? Because this is these women's weight and height right at the point where they got pregnant and went to Kaiser. And those who smoked until they were pregnant were smokers. And so I would also include, now this is different from what you did for your infant birth weight comparison. So it shows that what you consider a smoker can change depending on the particular situation. So I want to include those who smoked until pregnant. And then I'm going to call back that command and now say, all right, how about the never women? And oops, dang, I'll have to remake that. Oh, no, it disappeared. I don't know what I did to it. Okay. Never. And what was the other one? Once not now. You figured they're not smoking now, so let's just, this is debatable. I'm going to, what's that? The past is the past, right. So now I have my two variables, BMI for smokers and BMI for non-smokers. And I can say plot of density of BMI smoke. And did it again. I need to remove the NAs, and I need to spell true properly. So notice it said object TRU not found, and it's like, oh, right, it's TRUE. Okay, let me minimize this. There we go. There's the density plot for the smokers. Now, you might want to say, well, I want to make that look nicer. And I'm aware of the time, so I'm not going to make it look nicer first. I'm first going to show you what one of the first questions I got when I showed you my plot was, is like, okay, how do I stick non-smokers on that same plot? And there's a function called lines, and lines adds lines to an existing plot of density of BMI non-smoke. NA.RM equals true. And there it is. Now we have to be careful if these two have a very similar range in terms of the BMI and very similar range in terms of their density. If they didn't, one might be cut off, and so we would have to recreate our plots with specifying the limits in both the x and the y axis. Yes, question?
Could you also use the points function?
Yes, you can. Yes, you can. Shall we try that? You could, instead of lines, say points, and then say, what else do you have to say if you use points?
Well, if you want a line, you have to specify that.
Right, you say type equals L for a line, and that works. Now, I would like to actually try to, it's hard to, so this gets at clear vision. These are both black lines. And it's kind of hard to see which is which, especially near the peak. You could easily, and plus we don't know which one's for smokers and which one's for non-smokers once they're both there. So I'd like to now start taking this core plot and making it more informative. And that's what we're going to do. We're going to, let's use color. So now the color is not gratuitous. The color has a purpose. I would like to make the color of the one of the curves green for the non-smokers, and there it is. And I might say, that's so thin that when I'm displaying it on the projector, it's really hard to see. I'd like to change the line width, and I'll make that 2, which gives me a thicker line. So I can now also go back to my original plot and say I'm going to make this guy blue, and I'm also going to make the line thicker. And now I'm going to have a brand new plot, and I'm going to pull back my points, and there I've got pretty much the picture that I showed you at the beginning of the lecture, except that my labels aren't exactly right. And before I worry about my labels, let's figure out how to put that line that's the marker. There's AB line is a function. What's really handy in R is that when you call a function, it actually gives you all the arguments strung out there. And so you can kind of look and you can say, I can specify A and B. That's your traditional slope and intercept. But there's also an H argument and a V argument. So that's a special case where you just want a horizontal line or a vertical line. Then you just give it where you want to put that line. So I want a vertical line at the position of 30. And I can also have that one colored. And there are a whole slew of gray colors. And they come gray 20, 30, 66, whatever. I'm going to make this one gray 60. And there's my line. I also was trying to put a legend on my plot, and so I can say legend. And again, there are all of the arguments that you can use with legend. And I could say top right, or I can give it the exact x and y coordinate where it should be located. Legend equals. Now these are what I would like. This is now a vector of character labels. And so I create the vector with C for catenate, and I say non-smoker is my first, and smoker is my second. And now I want to associate that with some colors, and that's the fill attribute, or the fill argument, for the legend. Fill, again, a vector now of colors. The non-smokers were green, and the smokers are blue. And let's take a look. There it is. So we almost have the whole plot. The one thing I don't have is the text that says obese, and I have to fix up my title and my labels. And just really quickly, let me show you the text. There's text function, and you'd say where you want to put the text. So let's say I want to put it at 30 is my x coordinate. And how about 0.07 is my y coordinate. And the text is the word obese. And, oh, that's not what I expected. The default is to sort of center it at that point. I actually wanted it to start on the right. I could go into help and read about text, but given the time, I'll say I can read about it, find that there's something called an a POS argument, which says the position of it. And you can have, you can say that's sort of relative to the position you give, and 1 centers it. Hang on, let's try another one. How about 2? 2 puts it off to the right. Well, we could go with that. So notice what I'm doing is I'm not remaking the entire plot. I'm actually overplotting just so that I can figure out what's going on. 3 is, again, is above and centered, and let's see what 4 gives me. 4 is to the right. So I can now go back and recreate my whole plot really quickly. So I can pull up my plot call. Here it is, and just for fun, I'll say main equals BMI Kaiser. We'd want something a little more informative. And XLab equals BMI. And there we go. And now I'm going to put my points on here. There are my points, and which is my second curve, and then my legend, and then my AB line, and then my last thing, my text. And there you have it. There's the plot. So that's how you can build something up. I'm going to leave you with one picture. This is a picture I worked really hard to make. We're going to look at it on Friday. This is one of the worst graphs you could ever do. I'm quite proud of it. And so we're going to talk about how we can improve it, which is what one of the things you're going to be doing for your next homework assignment. So I'll see you all Friday.